In this example, we want to find the difference quotient of f. The difference quotient is defined by this expression here, f of x plus h minus f of x over h. H is not equal to 0. Division by 0 is undefined. And we want to find the difference quotient for this function here, f of x equals square root of x minus 20. We have a hint that says to rationalize the numerator, and rationalizing the numerator will be part of our simplification process once we find the difference quotient. So we want to find the difference quotient for this function, f of x equals square root of x minus 20, and our difference quotient, f of x plus h minus f of x over h, is square root of x plus h minus 20. So that's this first part of the difference quotient. Now minus our function f of x, so minus square root of x minus 20 over h. So this is the difference quotient, but we want to simplify it more. And that's where the hint comes in, to rationalize the numerator. Now to rationalize the numerator means that we don't want a radical in the numerator. So to get rid of the radical in the numerator, we're going to use a strategy of multiplying by the conjugate. So the conjugate, we're going to multiply by the conjugate. And the conjugate is the expression that we see in the numerator, except with a plus sign instead of the minus sign. So it has the opposite sign in between those two radicals. So we're going to multiply by square root of x plus h minus 20 plus square root of x minus 20. And we're going to do that on both the numerator and the denominator. And the reason why we're doing it on both the numerator and denominator is because when we put it in both the numerator and denominator, we're multiplying by a form of 1. And multiplying by 1 doesn't change the expression. So we're going to multiply by the conjugate. And in the denominator, we want to leave this expression in the factored form. So in the denominator, I'm going to leave this as h times that conjugate of x plus h minus 20 plus square root of x minus 20. However, in the numerator, I don't want to leave it in factored form. I want to multiply it out. And what you're going to see when we multiply it out is that some of the terms cancel out and some of the terms cause the radical to go away, which is our goal. Our goal is to rationalize the numerator, get rid of the radical in the numerator. So when we multiply, we'll multiply these two terms together first. Those are the first two terms. And when you multiply those together, so let's write it out. We have square root of x plus h minus 20 times square root of x plus h minus 20. When we multiply those two together, because they have the same radical and the same thing under the radicals end up canceling each other out. We'll take a look at that in just a few moments on the next step. So then we're going to multiply the outside two. That's going to give me a plus square root of x plus h minus 20 times the square root of x minus 20. Then we'll multiply the inside two together. It's going to give me a minus this time, a minus square root of x minus 20 times the square root of x plus h minus 20. Okay, I'm going to adjust here a little bit. And I hope that's within screen. Let's zoom out a little bit to make sure it is. And then we multiply the last two terms together. We're going to have minus square root of x minus 20 times square root of x minus 20. So that's what we get when we multiply it out. We're going to simplify some more. We're going to still leave that denominator in factored form. So we're going to leave that as h times square root of x plus h minus 20 plus square root of x minus 20. So let's focus on multiplying these two together. So when we multiply those two together, when you multiply radicals together, you multiply what's underneath them. And what's underneath them is the same, x plus h minus 20 times x plus h minus 20. So we can write that as x plus h minus 20 squared, and then underneath the square root. Now then let's focus on these two terms. If we look at this term and this term, this first one is positive and the second one is negative, and they have the same factors. So that means that they are like terms, but they're also opposites of each other. And we know that opposites cancel each other out. So those two terms just go away. They zero out. And then when we multiply these last two together, once again they both have radicals, and they have the same expression underneath the radicals. We're going to multiply those expressions together. X minus 20 times x minus 20 is x minus 20 squared, and that's still underneath the radical with a minus sign. And what we know is that square roots and squares are opposite operations, so they cancel each other out. So we're going to get x plus h minus 20. So we're getting that because the square root and the square are opposite operations and they cancel. And then on the next term, the square root and the square cancel each other out. And we're left with that x minus 20. But be careful, this minus sign applies to this whole expression. So we need to put minus in parentheses here to make sure that minus sign applies to all of those terms. And once again, we're leaving the denominator the same in factored form. And you'll see in just a moment why we did that. So we have h times square root of x plus h minus 20 plus square root of x minus 20. So now that the radicals are gone in the numerator, we're going to use distributive property to get rid of these parentheses. That's x plus h minus 20 minus x plus 20. We're leaving that denominator alone again. Square root of x plus h minus 20 plus square root of x minus 20. And in the numerator, we have some like terms. We have a positive x and a negative x. So not only are they like terms, but they're opposites and they cancel each other out. We have some more like terms, a negative 20 and a positive 20. Also opposites, they cancel each other out or zero out. And so all we have left in the numerator is an h. In the denominator, we have h times square root of x plus h minus 20 plus square root of x minus 20. And we have a common factor in the numerator and denominator that cancels, this common factor of h. will cancel out. And this is our final expression. We have 1 left in the numerator, and in the denominator we have square root of x plus h minus 20 plus square root of x minus 20. And this is our difference quotient for the function f of x equals square root of x minus 20. A rancher has 5,334 feet of fencing available to enclose a rectangular area bordering a river. She wants to use part of the fencing to create a partition to separate her cows from her horses by dividing the enclosure into 2 equal areas, as shown in the figure to the right. No fencing is required along the river. Let X represent the length of the center partition and complete parts A through D. So we have a nice picture of what's going on here. We have a river. The rancher is building these rectangular pastures bordering along the river, and she's creating them with this little divider called a partition in the middle. And that's so she can separate the cows and the horses. It also says to let X be that center partition. And that's the variable that's going to be used throughout. Now we want to create an expression that represents the length of the side of the fence that's parallel to the river. So that's this part right here. The length of fence that's parallel to the river, let's call that Y. Then we want to find the length of the side of the fence parallel to the river. If that center partition is 889, so they're going to give us a value of X, and we're expected to find the length of this fence here. We want to create a function that represents area. So it describes the area of these 2 pastures as a function of X. And then finally, we're going to find the area when that center partition is 889. So when we are trying to do this part A, which is to find the length of this side here, we are going to use something that is similar to perimeter. Now we have perimeter formulas for rectangles, but this has a little bit extra to consider because we're not going to use the side along the river. So we're using these sides as well as the side parallel to the river, and we have this extra partition. So we're using perimeter, but we're going to have to modify it because we're not using the river side and we have this extra side in the middle, that middle partition. So if we use the fact that these are rectangles, I know that this is also X and this is also X. So we have 3 sides that are X and 1 side that is Y. And those sides are where the fencing is going to go. So I know that that is going to equal, the sum of those will equal 5,334. I can solve for Y in terms of X by subtracting 3x on both sides. I have Y equals 5,334 minus 3x. And this is the expression that represents the side that's parallel to the river. Then if we want to find the length of that side, when we're given that the center partition is 889, we're given that value of X, we can substitute to get the value of Y, the side parallel to the river. to be 5,334 minus 3 times 889. We can do that with our calculator. So that's 5,334 minus 3 times 889, and that gives 2,667. And the units that we're using in this problem, let's see, are feet. So that's 2,667 feet. But then we want to create a function that represents area, the area of these two enclosures. So if we're finding the area, we're going to find the area of this big one here. And we can use our normal area formula, which is length times width. So our area function will be x times y, length times width, but we had an expression for y from part A. So that's x times 5,334 minus 3x. And we can use the distributive property to write this as 5,334x minus 3x squared. So now we have a function that represents the area of those enclosures. And then the last part here, we're now given that the center partition is 889 feet, and we want to know the area, so we can substitute that into our area function. Area of 889, that's going to be 5,334 times 889 minus 3 times 889 squared. So we'll use our calculator again to work that out. That's 5,334 times 889 minus 3 times 889 squared. And it looks like a really big number there. That's 2,370,963. And the units there would be square feet. Now there is a simpler way to get that value. We have the length and width here that we could just multiply together as well to get the area. So 889 times 2,667, let's see that in the calculator. So 889 times 2,667 also gives us that 2,370,963. So I wrote this backwards. So we get 2,370,963 square feet. For this question, we want to determine whether this graph is a graph of a function by using the vertical line test. And if it is a function, we want to find the domain and range, the intercepts, and any symmetry with respect to the x-axis, y-axis, or the origin. So let's start by determining if this graph is a function using the vertical line test. So the vertical line test has us drawing vertical lines. Let me use my ruler to draw the vertical lines. We're going to draw vertical lines everywhere we can imagine on the graph. And as we draw these vertical lines, what we're going to pay attention to is how many times the vertical line crosses the graph. So we can see that this vertical line crosses the graph once, this crosses once, this one once, once, and once. So every vertical line crossed the graph in one place. Now what this is telling us is that every x has one y. So because all of these vertical lines crossed in only one place, we have all of our x's for this graph have only one y, and that is the definition of a function. So if you have only one point where the vertical line crosses, then you have a function. If you have more than one point where the vertical line crosses, it's not a function. So this is the graph of a function. This is a function. So then we're going to move on to finding the domain and range. So I'll erase my markings and I'm going to get my ruler out to help me determine the domain and range. So when I'm finding the domain is the set of all the x's. I like to hold my ruler vertically and go from left to right. And the reason why I hold it vertically is because this ruler is marking along the x-axis. And as I said a moment ago, the domain are the x's, all of the x's for this graph. So I'm going from left to right, and I'm taking note of the first time my ruler hits the graph and the last time the ruler hits the graph. So at first glance, you might think that this spot here is the first time that the ruler is hitting the graph. But if you look a little bit closer, we have an arrow, and this arrow indicates that the pattern of this graph continues beyond what we can see in this picture. So this line will continue to go up and left beyond what we can see in this picture. And so because of that, we can see that my ruler actually will always be touching this graph on this side. And so that means the domain is going to start at -infinity. And then as we continue over here, the ruler continues to touch the graph. And at first glance, you might think that this is the last place that the ruler touches the graph. But once again, we want to take note of this arrow, which indicates that the pattern continues on. So that pattern will continue going to the right and up, meaning that this ruler will continue touching the graph as we go all the way over to the right. And so our domain is from -infinity to infinity. We're going to do something similar to find the range. To find the range, we're going to hold our ruler horizontally and go from bottom to top. And we're holding it horizontally because this will mark the y's, and the range is the set of all y values for this picture. I'm going from bottom to top, smallest to largest, because that's how we write interval notation. We always write smallest, then largest. So the first time I hit this graph will be at this value here, and I'm going to mark that on my y scale. And that looks like it is a -9. And then if I continue going up, you might think that this spot is the last spot that the ruler hits, but remember those arrows indicating that the pattern continues. And so I'm actually hitting the graph all the way to infinity. So our range for this example will start at -9 and go to infinity. And hopefully you noticed I put a bracket on -9. And I put a bracket on -9 because this point has a closed-in circle. And that means that it's part of the graph. And so -9 is part of the range. And that's how I indicate it with interval notation. A bracket means that -9 is part of the set. It is included as part of the range. So let's move on to the next part, which is asking for the intercepts. We have two types of intercepts that we want to pay attention to. We have x-intercepts and y-intercepts. An x-intercept is where the graph crosses or touches the x-axis. So here's our x-axis. It's their horizontal axis, and I'm noticing two spots where the graph crosses the x-axis. So this one looks like it's -5, and this one looks like it's +1. So we have x-intercepts at -5 and +1. If you need to write those in interval not interval notation, as an ordered pair, you would write the ordered pair -5, 0 and the ordered pair 1, 0. So the second type of intercept is a y-intercept. And a y-intercept is where the graph either crosses or touches the y-axis. And the y-axis is this vertical axis. And I can see that the graph crosses that vertical axis right here, and that is at -5. So we have a y-intercept at -5, and as an ordered pair, we would write that as 0, -5. And then we have our final part, which is looking for symmetry. Symmetry with respect to the x-axis, y-axis, or origin. So when you have symmetry with respect to the x-axis, I'm going to erase all this. Symmetry with respect to the x-axis means if you look along the x-axis, you want to have a mirror image above and below the x-axis. So if you were to fold along this x-axis, you would have these pieces of the graph falling on top of each other or matching up. And you can see that would not happen with this particular graph. So this graph does not have x-axis symmetry. So the next type of symmetry is y-axis symmetry. So we know where the y-axis is. It's this vertical axis here. And what you're looking for is a mirror image to the left and the right of that y-axis. So if we were to fold over that y-axis, we would need the pieces matching up. And you can see that this piece would not lay exactly on top of this piece here, meaning that we do not have y-axis symmetry. So then our final type of symmetry is origin symmetry. And our origin is the point where the x and y axis cross each other. So that's this point here, that's the origin. And when you have origin symmetry, a mirror image over the origin would mean that your opposite quadrants would have a mirror image. So I'm highlighting quadrants 1 and 3 to see if they have a mirror image, and then highlighting quadrants 2 and 4 to see if they have a mirror image. And I can see that we don't have a mirror image in these quadrants. If I just focus on this piece of the graph right here, I have a line with two endpoints, and if I look in the opposite quadrant, I have this curve right here, which has one endpoint and the other side continues on forever. So those do not mirror each other in opposite quadrants. So we do not have origin symmetry for this function. This question says use the graph of y equals f of x to answer the questions. For how many values of x is f of x equals -3? And what is the value of f of 2? Let's start with part A. for how many values of x is f of x equal -3? So we have to keep in mind that f of x is the same thing as y. So what we're really saying is how many values of x has y equal to -3. So to figure that out, I can go on my y scale to where y is equal to -3 and draw a horizontal line. And I want to think about how many times that horizontal line is crossing the graph. So this is the line y equals -3, and I can see right here I have a point on the graph, so there's one x value of -1. Here's another place where it intersects the graph. That one's not labeled. We could make a guess about it. It looks like it's about -4. And then we have one more place, and I'm going to erase here so we can see it more clearly. We can see that that's an open circle. And the open circle means that that's not part of the graph. So even though that's labeled on my picture here, because it's labeled next to an open circle, -9 doesn't count as a point on this graph, -9, -3. So we have two places where f of x equals -3. Two x values where f of x is equal to -3. So that's how many values of x, two values of x have y values that are -3. And for the second part where it says, what is the value of f of 2? We have to remember what this notation means. F of 2. 2 is my x, and f of 2, so this entire notation here, is my y. So what's asking me? It's asking me to say what is the y value when x equals 2. So I'm going to go to my picture. I'm going to find an x value of 2, and I'm going to go over to the graph to see what that y value is. And that y value is -1. So f of 2 is -1. On this example, we have a graph, and we want to find some information from the graph. We want to find the intercepts, if there are any. We want to find the domain and range. We want to find the intervals where the function is increasing, decreasing, or constant, and we want to determine whether the function is even, odd, or neither. Let's take these one by one, starting with the intercepts. So intercepts, you can have x-intercepts and y-intercepts. And an x-intercept is where the graph crosses the x-axis. So this is the x-axis, the horizontal axis, which I'm highlighting. And we're looking for places where the graph either crosses or touches the x-axis. So we can see that the graph touches the x-axis here, crosses the x-axis here, and touches the x-axis here. So these will be our x-intercepts. So we have x-intercepts at -pi, 0, and pi. Now you might be asked to write the x-intercepts in ordered pair form. If you are, you would write those ordered pairs as -pi, 0, 0, 0, and pi 0. You would probably separate them by commas. And then the second type of intercept is a y-intercept. And a y-intercept is where the graph crosses or touches the y-axis. The y-axis is this vertical axis, which I'm highlighting. And you can see that the graph crosses the y-axis at this location, and that is at 0. So 0 in this example is both an x-intercept and a y-intercept. in ordered pair form, that would be 0, 0. So that's the domain, those are the intercepts of this graph. So let's move on to finding the domain and range. Now the domain is defined to be the set of all x's. So what I'm going to do is I'm going to use my ruler. And I like to hold the ruler vertically. Maybe before we do this, I'm going to erase all these markings. Okay, so with my ruler, I'm holding it vertically to find the domain. And the reason why I'm holding it vertically is because this ruler is marking off x values when you hold it vertically. And remember, with domain, we're looking for the x values of this graph. So by holding it vertically, I'm paying attention to where the vertical line touches the graph. And if it's touching the graph, that means I have an x value. I have a part of the domain. So if it's touching the graph, that's an x value that's part of the domain. So let me erase these markings. And what I like to do is I'd like to hold it vertically and go from left to right across the graph. And what I want to pay attention to is the first time that my ruler, you might want to use a pencil, I want to pay attention to the first time that that vertical line hits the graph, and then pay attention to the last time that that vertical line hits the graph. And then you can use that, you can use those values in interval notation. So the domain starts at negative pi and ends at pi. And all the numbers in between are part of the domain, so we're using our interval notation to mark that. Now, as we look closer at these points, these endpoints are open circles. Not open, they're closed, they're filled in circles. So that means that the endpoints are part of the domain. And that we're going to use brackets to indicate that. So brackets means those values are included. So our domain of this graph is from negative pi to pi. So then we're going to rotate this ruler and hold it horizontally. And hopefully you see where I'm going, because the definition of the range are the y values, all of the y values on this graph. So I'm holding this ruler horizontally because if I hold it horizontally, it's marking out the y values along the y scale. And that's what I'm interested in when I'm looking for the range. So I'm going to hold this ruler horizontally. You can use a pencil. And we're going to go from bottom to top. And as we go from bottom to top, we're going to mark off the first time that my ruler hits the graph. So this is the first time it hits the graph. And then I'm going to mark off the last time it hits the graph, which is right here. And pay attention to what those y values are. So we have a y value of negative 7 and a y value of positive 7. And that's what I'm going to use for my interval notation for the range. My range will start at negative 7 and end at positive 7. Since these points are filled in circles or closed circles, I'm going to include negative 7 and positive 7 in the range. To include, we use brackets. So we have a range of negative 7 to positive 7. Okay, so I can see some of my markings over here are a little bit off screen, so I'm just going to put in here, I labeled this as domain, and I labeled this as range. So on the next part, part C, this is asking for intervals on which the function is increasing, decreasing, or constant. So these vocabulary words are referring to y, or trying to describe y. Each one of them is describing y. So what I want to do is I want to trace the graph starting from left to right, and that's starting from smallest to largest. So this is the leftmost portion of the graph. And I'm going to start tracing it, as I said, from left to right. And as I'm tracing it, I'm paying attention to the y values and whether the y values are increasing, decreasing, or constant. Now, as I'm tracing along this first section, I can see that the y values are decreasing. And then I get to this point here, and then the y values are increasing. And they continue to increase. The y values are increasing until we get to this point here. And then the y values are now decreasing. So I've found a few intervals of increasing and decreasing for this function. So I'm going to label them. So we said that this section right here, the y values are decreasing, and then also along this section here they were decreasing. And then we said along this section in the middle that the y values were increasing. So let's label that with decreasing, increasing, and decreasing. So now that I have it labeled, I'm going to pay attention to the intervals where the function is increasing, decreasing, or constant. Now these intervals are x intervals. So I'm going to bring out my ruler again, and since I'm looking for x intervals, I'm going to hold this ruler vertically, and I'm going to pay attention to this decreasing section, and I notice that the first time my ruler hits this decreasing section is here. I'm still hitting it, and then the last time it hits that decreasing section is here, which is right here. So I'm going to say that this function is decreasing from negative pi, let me give myself a little bit more room. It is decreasing from negative pi to negative pi over 2. So then we're writing our interval notation, and we need to decide whether we're going to include the endpoints or not. And this is sort of a debatable topic, and it's based upon how your book defines increasing, decreasing, and constant. I teach out of 2 different books, and they have 2 different definitions. One of them allows for the endpoints to be included, and the other one doesn't allow for the endpoint to be included. So you need to pay attention to whatever definition is used in your book to decide whether you're going to put parentheses or brackets on these endpoints. So in my college algebra class, we would put parentheses, but in my precalculus class, we put brackets to include the endpoints. So these are the intervals of decreasing. We have one more interval of decreasing over here. It's going to start at this spot right here and end at this spot right here. So that interval of decreasing is starting at pi over 2 and ending at pi. And then we want to mark out this interval for increasing. It starts at negative pi over 2 and ends at pi over 2. So we have an interval of increasing that starts at negative pi over 2 and ends at pi over 2. So we have one more part to go, part D, and we want to decide whether this graph is even, odd, or neither. So we need to know what those mean. An even function is a function that has y-axis symmetry. An odd function is a function with origin symmetry, and then neither is the category that catches everything else. So let's figure out what y-axis symmetry and origin symmetry look like. So let me kind of go in the middle here. For y-axis symmetry, what you would look at is this vertical axis, that's the y-axis, and if you have y-axis symmetry, you're going to have a mirror image on either side of the y-axis. So if I erase the markings that we see on this graph and just pay attention to the line, I'm going to look at the y-axis, and I'm going to look to the left and also to the right of the y-axis to see if there's a mirror image. And I can see that there's not a mirror image here. So in my mind, what I'm doing is I'm taking this piece of the graph and I'm imagining this graph as a piece of paper, and I'm going to fold that piece of paper along this y-axis. And if I were to fold this piece of paper, what I would get is a line that matches over here, but it does not match on top of the other part of this line. So we don't have y-axis symmetry, and so we can say that this is not an even function. So the other type of symmetry is origin symmetry. Let's take a look at what origin symmetry would be like. So I'm drawing the axes, and the x-axis and the y-axis cross at this point, which we call the origin. And when you have origin symmetry, you would have a graph that has a mirror image in the opposite quadrant. So I've just highlighted quadrants 1 and 3. And if you have origin symmetry, those would be mirrored. And then you would also have a mirror image in quadrants 2 and 4. So origin symmetry has a mirror image over the origin or in opposite quadrants. So taking a look at our example, the origin is right here where the x and y axis cross each other. And I'm looking in opposite quadrants to see if there's a mirror image. And it looks like to me there is a mirror image. I can see that in quadrant 1, I have a mirror in quadrant 3. And then in quadrant 2, we have a blank, meaning that there's no piece of the graph in that quadrant. And we also have blank in quadrant 4. So it looks like a mirror image, but if we want to be certain, we can think about folding the pieces of paper like we were doing earlier with the y-axis symmetry. And let me explain how you would fold the piece of paper to check for origin symmetry. So checking for origin symmetry, what you're going to do So if you're checking by imagining folding paper for origin symmetry, what you would do is fold twice. You're going to fold once over the x-axis and then fold over the y-axis. So I'm going to imagine this piece of the graph being folded over the x-axis, and you would get something that looks like this. And then if you imagine folding that new piece over the y-axis, it would fall right on top of the other portion of the graph. So we do have origin symmetry, and we can say that this function is an odd function. Thank you for checking out my videos. Have a great day.